Furry posted. Sure. I don't know if they. I don't think they'll pull it until next. Tomorrow. Continuing. So, modern atomic theory and the electron. Let's see, is this the correct? Let me look at this first. I don't think I start with this one. Yeah, I start with this one. Alright. So, investigating atoms and atomic theory. So, the word atom comes from the Greek word atomos, which means not to be cut. So, this is going to be the history of atomic theory. How recently do you think, when did we first discover atoms existed? How recently do you think, what year do you think we discovered the fact that atoms exist? Really? That late? Really? That late? So y'all think it's not relatively long ago? But then when did we know? Well, I guess you guys haven't discovered or haven't studied physics and everything. It's amazing how much we progress physics without even knowing about electrons. Like how much we understood electricity and having no clue that electrons existed. Like we had a very good model of what electricity was, and yet we had no clue what atoms and electrons were. Like Benjamin Franklin, whenever he started doing the kite experiment, he had no clue that it was actually like electrons flowing down and everything. It's relatively recent, but we had so advanced understanding of models. So atomic models. This model of the atom may look familiar to you. This is known as the Bohr model. In this model, the nucleus is orbited by electrons, which are at different energy levels. A model uses familiar ideas to explain unfamiliar facts observed in nature, and a model can be changed as new information is collected. So this is, for most purposes, going to be one of the models we mostly use. You can think of it like a solar system. We have, instead of the sun, we have the nucleus. Instead of planets, we have electrons. This is horribly wrong. It is nowhere close to reality. But it's, for purposes of this class, it's a good enough explanation in thinking about a few features of an atom. I will discuss a more accurate description of an atom and what electrons are and such, but it's very good to at least understand Bohr model. There's actually a major discussion of why we still teach this model because of how wrong it is and how very off from reality it is. But for most purposes, we can still think and use analogies like this. Just know that it's horribly wrong compared to how electrons and nucleuses and everything and how atoms work. So the atomic model has changed throughout the centuries, starting in 400 BC, when it looked like a billiard ball. So, we knew about atoms, or at least someone did, around 400 BC. over a 2,000 years ago, about 2,500 years ago, was whenever we first knew about atoms, or at least someone did. They thought that again, the word atom comes from ancient Greek, meaning unable to cut. So the great discoverers of atomic theory was actually only a few people throughout history. But we'll begin with 400 BC, the Greek philosopher Democritus. He began his search for a description of matter more than 2,400 years ago, and he asked a simple question. Could matter be divided into smaller and smaller pieces forever? Or was there a limit to the number of times a piece of matter could be divided? So he was a philosopher, and back then the greatest philosophers usually come up with thought experiments like this and try to investigate whether or not philosophically it would work out. He came up with this idea that could you continually cut a rope or some material into smaller and smaller pieces for all eternity, and there was no limit of how small you can get. His theory was matter could not be divided into smaller and smaller pieces forever. Eventually, the smallest possible piece would be attained. This piece would be indivisible or uncuttable, meaning that there was a limit to how small matter could get. He named the smallest piece of matter atomus, meaning not to be cut. If I go too fast, stop me. So, to Democritus, atoms were small, hard particles that are all made of the same material, but were of different shapes and sizes. Atoms were infinite in number, always moving and capable of joining together. So he thought of them as basically billiard balls, round spears, and the difference between atoms were their sizes. Other than that, one atom did not differ from another other than by its size. I guess he thought that they could also join together to make a bigger spear, or maybe connect together in some way. So this was back 400 BC. And this theory was ignored and forgotten for over 2,000 years. Any guesses as to why? You all know your ancient Greek history? You all know any history? 400 BC, over 2,000 years ago. Who were the prominent people? What were the prominent Greek philosophers? They're so famous that there's no possible way you have not heard of them. They're mentioned several times. I'm sure y'all know them. So name a famous Greek person, philosopher. Aristotle. Have you heard of Aristotle? Have you heard of Plato? So the top philosophers of the time was Aristotle and Plato. They were way more respected, and they thought that the world was created out of combinations of four elements: fire, air, water, and earth. Their theory was ultimately wrong, but because of they were so correct on so much more stuff and more famous, their theory won out over the idea of an atom. So Aristotle and Plato favored the earth, fire, air, and water approach to nature of matter. Their ideas held sway because of their eminence as philosophers, and the atomist idea was buried for approximately 2,000 years. So basically, their idea was that there was different concentrations of fire, water, and air and earth mixed together. So, for example, gasoline, being a liquid, had a water component, and because of its ability to catch fire, it also had some fire component. And if you were to take a match to it, you could separate the fire from the water, and I guess technically it has some air or whatever into it because it turns into a gas. But that was their idea behind it. Sand versus dirt would have different concentrations of earth, and so on, and that was how they thought the entire world was composed of. They also had a fifth element, spirit. Humans would have this fifth element, or what they called the soul, and so on, but it was their preferred theory, and everyone just supported them because they were ultra famous. So it wasn't until 1803, the early 1800s, that the English chemist John Dalton performed a number of experiments that eventually led him to the acceptance of the idea of atoms. So he deduced that elements are composed of atoms. Again, if I go too fast, tell me to go back. Atoms are indivisible, indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different. Compounds are formed by the joining of atoms of two or more elements. So this was, again, he's going from the universe is made of four elements, earth, fire, air, and earth, to this idea that there are atoms. Not only are there atoms of the same element are exactly alike, atoms of different elements are different, and they come together to make compounds by two or more atoms coming together. This is exactly what we have today. The core ideas of it, at least. He does get wrong that atoms are indivisible and indestructible. Also, atoms of the same element can be different, which we'll explore later. There's isotopes. So it's not quite the exact same. But this theory became one of the foundations of modern chemistry. He also, John Dalton, bless you, he also thought of atoms as being billiard balls, round spheres. Next, we get Thomas Plum Pudding model. So in 1897, not quite 100 years later, the English scientist J.J. Thomson provided the first an atom is made of even smaller particles. So before Thomas, they thought for 100 years he had this idea of an atom now. They thought that all atoms were identical and that they were the smallest thing ever. He proposed that a model of an atom that is sometimes called the plum pudding model. So he ended up discovering electrons, and that electrons were a part of the atom. He discovered that, or he provided the first hint that atoms are made of even smaller particles, and he discovered the electron. So if the atom has electrons, and these electrons are negatively charged, He postulated that the atom must be filled with a positive substance to counteract the negative charges of the electron. So in this plum pudding model, atoms were made of a positively charged substance with negatively charged electrons scattered about it like raisins in a pudding. So he thought of the atom as being a positively charged substance, where the positively charged substance is uniformly spread out over the atom. Think of it like gelatin that's positively charged, and electrons are randomly scattered throughout it. He discovered this by studying the passage of electrical current through a gas. Again, they've known about electricity for a long, long time, but they had no clue what an electron was. As he passed current through the gas, it gave off rays of negatively charged particles. So he was able to detect that there was this negative particle coming off when he runs electricity through it. And this is a very surprising result. How can an electrical particle be given off when you run electricity through it? Again, they had no clue of the concept of an electron. They knew that positive and negative things existed. You can have a positive and a negative terminal on a battery, but they had no clue what an electron was or the components of an atom. What was surprising about this was the atoms of the gas were uncharged. So how could something negative come from something that doesn't have a charge? Where could these negative charges have come from if the material was completely neutral? It was from this he concluded that the negative charges must have came from within the atom. That a particle smaller than an atom had to exist, and that the atom was in fact divisible. I'm very glad this name did not keep up. Originally, the electron was called a corpuscle. Corpuscles. I don't know how you even pronounce that. Doesn't matter. It's a hard name to pronounce. We now call them electrons. But since the gas was neutral, having no charge, he reasoned that there must be positively charged particles in the atom, but you could never find them. I'm not for sure if he thought they were particles or if he thought it was a substance filling it. Often, this model is often thought of as it being a positive liquid or substance that filled the entire atom, with electrons being particles. But at the same time, they like calling everything a particle, physicists do. So he was never able to find what positively charged particle was. Next, so this was 1897. In about 10 years, a little over 10 years, Rutherford started doing experiments. Ernest Rutherford in 1908, an English physicist, was hard at work on an experiment that seemed to have little to do with unraveling the mysteries of the atomic structure. I will also tell you all this, that a lot of these people, they get the credit, but a lot of their students did all the work. He's often credited with it, but I want to say that his research student was the one that did most of everything. Still, he gets all the credit. So, what he did was fire tiny stream of positively charged particle at thin sheet of gold, 2,000 atoms thick. If you didn't know this, gold is one of the most valuable substances in the world. If you were to get a gold ring, if this pure gold and get a hammer, you could hammer it to only a few atoms thick. You can sit there and bang it over and over until it's only a few atoms thick. Most substances would break before getting to this, but gold has the ability, it's very malleable, to be hammered that thin. These tiny particles he are shooting, all he knew that they were positive. They're technically called alpha particles. So an alpha particle is the nucleus of a helium, 2 protons and 2 neutrons. Thus it has a positive charge of 2 because of the 2 protons. And he's firing at a thin sheet of gold foil. So this gold foil is 2,000 atoms thick, and he's basically shooting 1 helium nucleus at it. And he's doing it at crazy high speeds. This is often described as being equivalent of getting a 9mm pistol, walking up to a piece of paper and shooting it. The amount of energies the alpha particles were being emitting at were crazy high. So it was a very high energy being shot. And he's shooting at something like a piece of paper. And then after you shoot the piece of paper, you see a bullet ricochet off of it. This was extremely bizarre result. Surprising. This was extremely surprising, as there should be no possible way of it to actually bounce off of something so thin with that much energy. Most of the positively charged bullets pass right through the gold atom of the sheet with gold foil without changing course at all. So looking at like A, most of them would go through. Some of the positively charged bullets, however, did bounce away from the gold sheet as if they hit something solid. He knew that positive charges repel positive charges. He was expecting things to be like what's labeled as B in this diagram. He was expecting to detect a small amount of curvature, as these positively charges are deflected in certain angles. He did not expect any of the particles to actually bounce backward. And he knew that in order for it to actually bounce off, you have to have a very concentrated positive charge. So what he ends up discovering is the nucleus. He discovers the fact that the atom has a highly dense positive region, which he named the nucleus, and that it was at the center of the atom. So this could only mean that the gold atoms were mostly empty space, and the atoms are not a pudding filled with a positively charged material. He concluded that atom had a small, dense, positively charged center that repelled his positively charged bullets. He called the center of the atom the nucleus. And the nucleus is tiny in respect to the atom. So his model completely changed the idea of an atom. So the atom is now empty, completely empty, with a positively charged nucleus. And the nucleus is extremely tiny compared to the atom as a whole. Rutherford reasoned that all the atom's positively charged particles were contained in the nucleus. The negatively charged particles were scattered outside the nucleus around the atom's edge. So in his model, he thought the electrons were all on the surface, at some radius away, which is wrong. But this was the very first step into discovering the nature. We then go up to Bohr model. In 1913, Danish scientists. So again, this is so in 1897 we discovered atoms. In 1908 we discovered in early 1800s we go from atoms exist. 100 years later, atoms have positive and negative charges in them. Only 100 years after that, no, it's not, 10 years after this. So within 10 years, we now discover the shape of an atom, positive nucleus, electrons on the outside. And only a few years after this, the Danish scientist Niels Bohr proposed an improvement. In his model, he placed each electron into specific energy levels. According to Bohr's atomic model, electrons move in definite orbits around the nucleus, much like planets circle the sun. These orbits or energy levels are located at certain different distances from the nucleus. So we have these energy levels. Basically, energy level is going to be the distance from the nucleus. So atoms that are really close to the nucleus are at lower energies, or energy levels. And as you increase the radius, you're increasing the energy. And electrons can only be at certain energy levels, or certain radius from the atom. And they orbit much like a planet orbits the sun. And this is a very common model. This picture is what you probably think of when you think of an atom. You think of electrons orbiting around a nucleus. However, that is not the correct model. The correct model is the wave model. Today's atomic model is based on the principle of quantum mechanics, or wave mechanics. According to the theory of quantum mechanics, or wave mechanics, electrons do not move about an atom in a definite path, like planets do around suns. So an electron doesn't actually orbit around an atom. It doesn't orbit, it doesn't move around. It is extremely complicated. In fact, the electron doesn't even really exist. At least not how you think of it. You would not say an electron doesn't exist as an electron. It more accurately exists as a wave. In fact, it is impossible to determine the exact location of an electron. Instead, we have a probability we have a description that tells us the probable location of an electron, and it's based on how much energy the electron has. According to modern atomic model, an atom has a small positive charged nucleus surrounded by a large region in which there are enough electrons to make it neutral. which gives idea to the electron cloud, is the space in which electrons are most likely to be found. You really wouldn't say electrons whirl about the nucleus billions of times in 1 second, because they are not moving around. I mean, you really can't say an electron has a location, not a single location at least. The electron cloud is the region in which there's a 90% chance of finding the electron there. So it's a region or a volume in which there is 90% chance that if you look in that volume, you'll find the electron. And it'll be randomly in there. You really can't say it's moving around or orbiting around the nucleus. You really can't say it's moving at all, other than it most definitely is moving. Because the conservation of momentum is mass, so there has to be some momentum. However, you have no clue what that momentum is. Quantum mechanics is extremely weird. So depending on their energy, they are locked into a certain area in this cloud. Electrons with the lowest energy are found in the energy level closest to the nucleus. Electrons with the highest energy are found in the outermost energy levels, farther away from the nucleus. So, quick little summary. Trying to see if that's easy. I don't think there's anything on that stuff. No, there isn't. So, Greek and Dalton thought that atoms were invisible. Thomas discovered the electron. Rutherford discovered the nucleus. And thus the proton. I think it's safe to say that Rutherford discovered the proton. He's credited he at least discovered that there was a nucleus that had positive particles in it. Bohr thought that there was orbits, and the wave or quantum mechanical model. Erwin Schrödinger is credited with that. So Erwin Schrödinger is credited with the wave model. Again, worked on quantum mechanics. To give you an idea of the bizarrety of quantum mechanics. So let's say that we have an electron in a box. The electron does not exist. not as a particle. So, electron does not exist as a particle until we look at it. I.e., do a measurement. Instead, we have something known as the wave function. This wave function is, first of all, imaginary, and if we take the square of it, it tells us the probability. When I say it's imaginary, I say it's an imaginary number. I'm sure y'all seen probability of position. So if we take, and this is Greek letter psi, this is the wave function. And this is the Copenhagen interpretation. So anytime we look in this box, we might find the electron right here. I'm assuming this is one-dimensional, that's all on this bottom line. Most of the time, we'll find it right here. We keep looking. Occasionally, we'll find it over here. We keep looking more. Find it there. So we keep looking in this box, and every time we look at it, it's in a random different spot. The most likely place to find it is directly in the center. Center, if this was the wave function of the electron. And also right here is the second most likely place to find it. And so if we look at the first orbital, another name for orbital is energy level. So we have the nucleus. And if we were to look and ask ourselves, where's the electron around this nucleus? Well, we look at it. Right there. Look at it. And we keep looking at it. What we end up happening is we form a sphere. Of where the electron is. So the electron, the first orbital, is in a sphere shape. And again, we have no clue what the electron is doing, because when we are not looking at it, it's a wave. When we do look at it, it collapses to a random point, a single particle, and this wave function just simply describes the probability of finding it. So, for example, this could be 50%. So there is a 50% chance that it's here. There's a 25% chance it's here. There's a 25% chance it's over here. So if you do this 100 times, what you expect is 50 times it'll be here, 25 times it'll be here, 25 times here. Here, same thing. 90% of the time it's in the sphere around the nucleus. That is the first orbital. There's only one, called 1s. There's only one first orbital. Let's look at the second orbital. The second orbital, or I should say, second energy level. The second energy level has two types of orbitals, 2s and 2p. 2s, let me use another pen. 2s is another sphere that is bigger because it has more energy. So again, every time you look at the atom, so it's a bigger sphere. And there are 3 2p orbitals. And yes, we're going to learn all this. So don't think I'm just telling you this for no reason. This is important to know. Let me redraw. So here's a nucleus. So 2p1 looks like this. So we take a measurement. Electrons right here. Take another measurement. Electrons right here. Take another measurement. The electron teleports over here. Note the electron cannot go through the nucleus. It just randomly exists on the other side of the atom. So anytime we look, it's just randomly in a spot. There's no movement from this location to this location because it's impossible. You can't just go through the atom or nucleus, but we keep taking measurements over and over and over again, and we get this dumbbell shape. That is the 2p1 orbital. There is also this orbital, 2p2, and since this is 3 dimensions, we have one in this shape too, like that, and that would be 2p3. So let's look up electron orbitals. So there's 4 flavors. There's the S ones, the P ones, the D orbitals, and the F orbitals. There's energy levels. So we could have a S orbital in the first energy, second energy, third energy, and so on. So here's a 1s, 2p, a 3d, and a 4f. And here we can see the 3 types of 2p orbitals an electron can have. Again, it can't exist in the nucleus. So this pink region is a orbital. The electron is just randomly in it. And this is the probability of 90% finding it in here. Because this extends much bigger than it is, but this is just a concentrated view of it. It's more fuzzy than this. That's why they usually take the 90%. So if you thought atoms were very smooth, and if you're curious on what the equation looks like to solve this shape, so here's the wave function. Oh, that's already solved. But we're going to be analyzing and writing down these orbitals of where the electrons are in and writing rules. So there are rules on where the electron can be, which orbital it can be in, and this discovers this basically makes up what an atom is. So here's the d orbitals. as you keep adding more and more electrons to the atom, and they start filling these orbitals, you get the fact that the atom looks spherical as they stack on each other.